These are the notes on conservation of momentum. So we already talked about what momentum is. It's kind of like what keeps something going when it's moving, and it's represented by the letter P for petere in Latin. P equals mv, mass times volume. Very easy equation. Not the same one for energy, please note, but it's a pretty easy equation to use. Now, what can we do with this equation? Here we go. So we already talked about how momentum comes from the Latin word for movement, movimentum, and it gradually changed into momentum. And that is sort of the power of motion, right? What keeps you moving. Now, what about conservation? Well, a lot of people think of conservation as saving the environment, as conserving, keeping, or protecting, guarding nature. And it did actually mean that even before they started using it in the way we use it in physics. In fact, it meant preserving your health, preserving the environment, safeguarding, protecting, all of those things. Okay? But the way we use it today in physics dates all the way back to the conservation of energy, which was the first conservation law that was observed by Leibniz. And oh, I think they misspelled Leibniz's name here. Yeah, they did. Do you know why? How I know that? Because I misspelled it like that once. It seems like it should be spelled like that, but there's no T. It's Leibniz, N-I-Z. I'm pretty positive. That's funny. So this is from Etymological Dictionary Online, online etymology, and they're usually really good. That's crazy. Anyway, whatever. So he thought of it as conserving sort of the stuff of life. Okay, what dreams are made of, kid, right? He considered energy what made things move, like living things. So that's how he thought about it. He sort of had a interesting take on it, sort of almost metaphysical. And he was a really interesting scientist. He actually proved Newton wrong on one thing, so Newton did not like that. But anyway, that's where conservation in this sense, in the sense of physics, comes from. So there are many conservation laws that have been discovered since then. And whenever there's a conservation law, you can call it a zero-sum game. So what does that mean? A zero-sum game is a game where there's only so much of something. So if somebody wins, then somebody else has to lose. You're not making new stuff, making more of it. So there's a lot of zero-sum games. We can represent them mathematically like this. A initial plus B initial equals A final plus B final. So you might say, well, why is that a zero-sum game? Where's the zero? So I could rearrange it. If you really need your zero, I can rearrange it like this. And now you got your zero, although now it's not a sum, it's a subtraction. Well, anyway, whatever. It's summing a negative, whatever. Think of it that way. And I guess you could think of the dash in zero sum as being a negative sign, maybe? So a zero sum game is where if somebody wins, somebody else has to lose. Or if somebody gains something, somebody else has to lose something. Not really somebody, but something. So if some object gains momentum, for example, well, then some other object must lose momentum. That's what a conservation law means. So let's look at other conservation laws. Let's look at a list. There's quite a few conservation laws. There's conservation of energy. That's a big one. That was the first one that Leibniz talked about. Leibniz without a T. Pretty sure about that. Conservation of mass. Well, that's the law in chemistry. Lavoisier discovered that one. Big one in chemistry. You could almost say that is chemistry, the conservation of mass. Now, the conservation of mass can be violated, and that's because energy and mass are sort of manifestations of the same thing, in a way, or they can be. So some people consider the conservation of energy and mass as one conservation law. That's why I sort of put them side by side there. And you can violate the conservation of mass with nuclear reactions. So there you go. That's the dirty secret of chemistry. Okay, and then there's conservation of linear momentum. That's the one we're talking about. When I say conservation of momentum on its own, that's the one I'm talking about. Linear momentum. Okay? And then there's conservation of angular momentum, which is another one. That's another kind of momentum. Hopefully we'll have time to get into that one too. Then there's conservation of electric charge, conservation of baryons, basically like the quarks, conservation of leptons, well, that's basically like electrons, muons, and tau particles. Anyway, don't worry about those. Those have to do with quantum physics more than the kind of physics we're doing right now. So the main ones that we're going to encounter, let's say in high school science, are conservation of energy and mass, of course. You've already seen those. Conservation of linear momentum and angular momentum. And maybe electric charge. Yeah, that one too. So those are the ones we're going to be dealing with. But right now we're focused on conservation of momentum. Remember this one from chemistry? You should definitely remember this from chemistry. The conservation of mass law. There's not that many laws in chemistry. And this is the overriding, overarching, number one big law that has to do with understanding chemistry. The mass of reactants is equal to the mass of products. You're not going to lose atoms in the shuffle. Atoms are not created or destroyed in chemical reactions. Now remember, I did say this can be violated in nuclear reactions. And then there's also the conservation of energy law that actually Leibniz proposed. This is actually even better than conservation of mass. This one is not violated. This one is always true. So energy is not created and it is not destroyed. Energy can be transferred and transformed into different forms. It can be stored in matter. It can be stored in the movement of matter. It can be in a relatively pure transmissional form, like in electromagnetic radiation. But if you add all that up, it's a zero-sum game. And if you included all the energy in the universe, well, then I guess it's just zero-sum game for the whole universe. But usually we confine ourselves to a system. We talk about what is contained within a certain limited boundary, certain limited system of objects that we're keeping track of. And that's generally what we have to do because our minds are not infinite. So here's the new one, conservation of momentum. It's kind of just like the other ones. The total momentum of all the objects before an interaction is equal to the total momentum of all the objects in a system after that interaction. Now, obviously, this would be true for the whole universe. If you could find the momentum of every object in the whole universe, and if you monitored them from time to time, they would still add up to the same value from one moment to the next. But we can't really handle that, so we limit ourselves to a small system, maybe 2 objects, maybe 3 or 4 objects, just a limited number of objects with nothing coming in or out of that system. And it's much easier for the human mind to grasp. So conservation of momentum is a pretty good law of physics. There we go. Boom. So how do we represent it mathematically? Well, just like I had before, AI plus BI equals AF plus BF. Well, conservation laws are pretty much always like that. The only difference here is now we're talking about momentum, which is represented by the letter P, remember. So PAI, that would be the initial conditions for the momentum of object A, right? Get it? Plus PBI, which would be the initial conditions for the momentum of object B in a system, is equal to PAF, the final momentum of object A, plus PBF, the final momentum of object B. So in other words, momentum can be transferred from one object to another, but if you take the sum of all the objects in the system, it remains a constant. That's what this is saying. Okay, that it's a zero-sum game. If somebody's going to gain momentum, well then somebody's got to lose momentum. But the thing about this is, remember that momentum is a vector. So you could gain momentum in one direction and it would be sort of a negative momentum in the other direction. So you'll see what I mean in my examples. Another way to write the conservation of momentum, now this one is even longer, but this one is sometimes more practical because remember, the mass of A is not going to change from initial to final conditions. So the mass of A is just the mass of A, and it's written twice, once on each side. The mass of B is not going to change unless, I guess, you chip a piece of it off or something between initial and final conditions. So you don't need initial and final masses. Those are going to remain the same. What is going to change is the velocity. Okay, so if you know information about the velocities rather than the momentum, okay, now notice that this basically is saying the exact same thing we just had, except for now we're splitting it up into the mass and the velocity. Okay, in the first one we'd combine those because remember, mv equals p, right? So if I multiply the mass of A times the velocity of A at initial conditions, that is PAI, right? So this is just an expanded form of it. If you just know the masses already and you want to find out the velocities going in and the velocities coming out. So the point of this again is that if somebody gains momentum, well, somebody better lose momentum. Okay, it's a conservation of momentum. It's a zero-sum game. You can't get momentum out of nowhere, is another way to say it. Momentum is neither gained nor lost in the system. So the point of conservation of momentum is that whatever the object's initial momentum is will remain in the outcome. If two objects interact with each other, let's say collide, well, you know Newton's third law, action-reaction, well, the momentum can be transferred from one object to the other, or it can be partially transferred or distributed between the two objects, okay? But if you add the momentum of the objects afterwards, it will equal the momentum of the objects initially. So PAI plus PBI equals PAF plus PBF. The initial momentum, the sum of the initial momentum is equal to the sum of the final momentum. But this only works in a closed system. What is a closed system? Well, when no balls are lost and no balls are gained, let's talk about collisions of baseballs or bowling balls. Such a system which does not gain or lose mass is a closed system. Another thing you need to be a closed system is that there are no net forces acting on the system by objects outside of it. Oh, like the Earth, like gravity. So sometimes that can mess up your closed system. Under the conditions of a closed system, the law of conservation of momentum states that the total momentum of any closed isolated system does not change. So again, if you were able to encompass the entire universe, well then you could make it an absolute statement. The overall momentum of everything in the universe is not going to change. Okay, but we can't deal with all that. We have to focus on a system. And it turns out the conservation of momentum only works in what we call a closed system, okay? Because otherwise we would have to keep on going and add in the momentum of the Earth and so on, and it would get out of control. So really, honestly, for reals, no system on Earth can be said to be absolutely isolated, because there's always some interaction between systems and its surroundings. Like think of field forces. They just don't stop. So often these interactions are small enough to be ignored when solving physics problems, or at least we do that anyway, even if they're not small enough to be ignored, just because it gets too complicated, okay? So now, one way to isolate this is not to have any vertical problems, any problems that involve acceleration due to gravity. If you already have something on a flat surface, well then you know the normal force is balancing the gravity. So then that has no net force. There's no net force due to gravity. Okay? But really, honestly, there's almost always something operating from the outside, at least field forces. So when we do the conservation of momentum, we like to consider that the sum of the initial momentum is equal to the sum of the final momentum. Actually, the plural is momenta, but that sounds weird, okay? But practically speaking, what can we measure? We can measure the masses of the objects and their velocities at the beginning and their velocities at the end. So if you look at the one on the top, there's only 4 variables, those 4 P's. It turns out if you want to solve a conservation problem, you need to know 3 of the 4. You need to know, usually we know the 2 initial conditions, and 1 of the outcomes, 1 of the final ones. Then we can solve for the other. If you don't know either of the final conditions, well then you could try to make a prediction, but it turns out there are many possible outcomes. So we try our best, but if we have 3 of the 4, we can definitely solve it. And if we have 2 of the 4, we can make sort of predictions, but they've got a range, okay? And so because we measure mass and velocity, we often wind up using the one on the bottom. Notice that that's the same thing as the one on the top. Because what is momentum? What is P? It is mass times velocity. So if you substitute those, it turns out to be the same exact equation, just sort of expanded. So this is the problem I'm going to do in my example, and I will explain there. Okay, I'm going to do this example, but I just want to point out, now that I have this video going, we're talking about momentum, and the conservation of it, the conservation of momentum, okay? What are we really talking about? So if an object is moving, we're going to be talking about 2 cars represented here, 2 cars moving. They have sort of the mass and velocity that they have that's carrying them on. Let's think of it that way. It's what keeps them going, all right? Now, when 2 objects collide, that momentum can be transferred. Here we have 2 hydrogen models on sort of a track. Now watch what happens. Now, some of the momentum from this ball was transferred to that one. What if I roll them toward each other? Okay, this one actually transferred its momentum into reversing the direction of that one. Okay, let's do one more. Okay, same thing, same outcome. And what if the objects have very different masses? Well, here we have a very, very heavy magnetic ball and a ping pong ball. Hopefully this will stay on the track. Let's see what happens if I collide it this way. It sort of bounces off. It doesn't really budge that one. Okay, what about if I do it the other way? Okay, now notice this one sort of bulldozes the other one. So if you have more mass, you have more momentum. Okay, even if you're going at the same velocity. And then in the situation of the car, what we have is, well, let's say we have 2 objects that are going in the same direction. One is going slower, and then the other one catches up to it. So they could collide and bounce off, but what we're going to have is afterwards, they're going to be a combined mass. So then we're going to consider their masses together. So we start off with 2 separate ones, and then they sort of get stuck together. Sometimes cars do that when they collide, not always, okay? And one more thing I want to mention before I get to the actual problem is about Newton's cradle. I did get another Newton's cradle, okay, to replace this one. Okay, this one had a little bit of an issue. Ian! Okay, so I got a much better one, boom. And the thing about Newton's cradle is we were talking before about action-reaction. It does show you action-reaction. But another thing it shows you is the conservation of momentum. But it's a little bit complicated because it also involves gravity. Because when this ball, let's say it gets knocked off this way, well, what's going to stop it from moving? Okay, its weight is going to stop it. And then that's going to reverse its direction and bring its momentum back in. Then the momentum is going to get transferred through to the other side, and then gravity causes the reversal again on the other side. So when you release a ball, and if they're all in good formation, you sometimes get this. So the momentum is being transferred back and forth, and it's reversing directions because of the gravity. Now remember, momentum can be positive or negative, and the momentum can be distributed. If I do this a little sloppily, I can probably get the momentum distributed sort of between the different balls. See now, it's being spread out between them. It's not all in one ball. Okay, another way to do this is you try to do 3 at a time. Okay, so you sort of see how the momentum is being transferred. So momentum can be transferred, okay, but it is conserved. So whatever amount of momentum you had to begin with is the amount you still have later. You continue to have it. Okay, so I'm going to move this apparatus. Now, here's the problem. A 1776 kilogram car, 1,776, car going at 25 meters per second. Rear ends, that's not very nice. That's happened to me. Not very nice. A 1,066 kilograms, 1066. These are two important dates in history if you're a history buff. Kilogram compact car. So the first car is more massive. The second car is lower mass, okay, and it's smaller. Going 16 meters per second on ice. Now this is important because ice has a very low friction, which is one reason why driving on ice can be so hazardous. Well, this is not a very Southern California question, okay, but a lot of times we try to find ways to eliminate or minimize the friction. So here you go, that's a good way to do it. In the same direction. The two cars stick together. Let me read that again. A 1776 kilogram car going at 25 meters per second, rear ends a 1066 kilogram compact car going at 16 meters per second on ice in the same direction. The two cars stick together. How fast do the two cars move together immediately after the collision? Okay, that's before friction has time to slow them down. Let's say there is some friction. Okay, so the thing about this is obviously the car that's in the front needs to be moving more slowly than the car that's in the back. Kind of like this. Oh yeah, that works. Okay, let's try it again. The blue car wasn't moving. Yeah, that worked pretty well. And then they were traveling together. They didn't get stuck together, but they just happened to stay together. So think about they each have their own masses, A and B. Okay, they each have their own velocity, VA and VB. This is the initial velocities, VAI, VBI. And then after they get stuck together, well, really, it's just one big mass. It's A plus B, and they both have the same velocity, at least immediately after. So what equation are we going to use for this? Well, obviously, conservation of momentum, right? So we're going to use the momentum of one car plus the momentum of the other car is going to be equal to the combined momentum of both cars afterwards, okay? But the problem is we don't have the momentum of any car. We're going to have to calculate it. So sometimes it's more practical to use this other version. This is the same thing, by the way. It's just breaking it down because remember, P equals mv, right? P equals mv. So you could put mv in place of each of the p's, and that's what we've done here. So it's a lot of variables here, and but it's sometimes easier to use this one. Okay. Another thing you can do, by the way, is you can use this half of this one, and then that half of the other one. Right? You can start off with this, and you can end up with that. Or vice versa. You could do it this way. Start off with this one, like this, and end up with that one. You can do that. That's fine. Okay, by the way. So in a way, we're going to do that because we can calculate these two. And once we have those, we're going to add them together. But then on this side, we're going to leave it more like this. Now, there's one other variation here, because normally, guess what? This would not be enough information. This would not be enough information to solve this problem. Except that they wind up stuck together. Because normally what you need in, let's say, a 4-variable problem, you need 3 of the 4. You can only solve for 1, okay? And in this case, well, this gets more complicated because it's split up into different terms, so it's not as obvious. But I really couldn't normally solve this one with only these two, okay? But because their velocity at the end is the same, the VF, the VAF and the VBF are the same number, well then I can solve it. That's what gets me out of this problem. Okay, so let's write down the numbers that we need. Let's start off with, I think I'm just going to use this one, okay? So let's start off with the numbers that we know. I'll write it right up here, is good. We're going to consider car A, okay, this car A and this car B. By the way, obviously,
car A needs to be going faster than car B if it's going to catch up to it and collide with it. So obviously car A has to be the faster car and car B has to be the slower car, just to make sure you realize that, okay? And the mass of car A is 1,776. Oh, is this the right unit? Is this what I need? Ooh, well, momentum is measured in kilograms, meters per second. Yes, so that is, kilograms is fine. kg, okay? And I'll just put that into parentheses. And it's going at 25 meters per second. That's my VAI. Is that the right unit? Yes. So this is not one of those problems where you have to convert your units. It gives it to you in the right form. So that is actually this. Okay, just that. Now I'm going to put plus, and I'm going to take the mass of car B, which is 1,066 or 1066 kg. It's in the right units. And the velocity of car B, the VBI, the initial, this one, the VBI, and that is 16 meters per second. So you might think, oh, he's running out of room, but actually on this side, we're going to write we're just going to leave it like this. So I'm going to write on this side, I'm going to write equals, and it's going to be the mass of A times, I'm just going to write VF, because remember, it's going to be the final velocity for both cars, okay, plus the mass of B times VF. Now, I could write VAF and VBF, but we know those are going to be the same, so I'm just going to write VF. So get it? That's the one reason we can solve this problem with this little bit of information, because those two are going to be the same. If not, we could not solve this problem, by the way. Well, you could make a prediction, but you couldn't get, it's harder to get a result unless you have 3 out of 4. Okay. So let's multiply over here, and now this is going to give me, these two multiplied together is going to give me my momentum of A initial, okay, because m times v gives me P. Okay, so let's multiply those. And 1,776 times 25 equals, okay, 44,000. And what are the units of that? Kilogram meters per second. Okay, so now we've got the other one, and that was my, of course, now we've got the PAI. That's my initial momentum for this car. Okay, then let's do this one over here. 1066, Battle of Hastings, 1066 times 16 equals 17056. And it's kilogram meters per second. And let's put the comma in right there. So is it surprising that this one has so much more momentum than this one? Is that surprising to you? Okay, shouldn't be, because this car is more massive, that's one reason, and this car is also going faster, that's another reason. So for both reasons, it should have more momentum. If we add these together, it's the total momentum going in, the total initial momentum. You could say the PI, the initial momentum. Okay. And then on this side, well, for now, you know what I'm going to do? I'm going to simplify this, because VF is the same number. So we could, since these are multiplied by the same variable, I could have MA plus MB times VF on this side. Okay? And those are numbers that we have. Okay? So we can add those in the next round. Okay? Oh, I guess I should have written them in there. Okay, so let's add these together. I've still got 17,056 plus 44400 equals, this is my total initial momentum. So it's 61,456, same units. Okay, obviously when you add, that doesn't change units. Adding doesn't change units. And then that is going to be equal to, now let's put the masses in here. You know what, why don't we just, I'm going to write them in just so you can see that stuff. Okay, so we've got 1776 kilograms plus 1066 kilograms. That's the mass, and I'll put the commas in. Gotta be careful. And it's multiplied by VF. So now that's our unknown variable. Okay, so let's do the next step. Well, this is going to stay the same. I'll just rewrite it. 61,456 kilogram meters per second equals, so let's do 1776, the start of the revolution. Okay, a lot of people don't realize that the revolution lasted for 8 years. People think, oh, it just all happened in that year. No, it didn't. Okay, plus 1066 equals the Norman invasion. 2,842 kilograms. Okay, and then of course that is still times VF. Well, we want to be nice to VF. We want to give it its own space, give it its personal space. This is the personal space show. So we've got to get rid of whatever is attached to it. So what we have to do is we divide both sides by the same thing. It's an equation to be fair, and we divide it by the little pestering thing that is attached to it, if that's the right word. That little annoying attachment wants to get rid of it, be on its own. Its roommate, I guess. That's its roommate. Okay, so these are obviously, these are going to cancel. The units are going to cancel. So then we have to divide here, and then that is going to give us our VF. So hopefully it comes out in the right units, right? We're solving for VF. Now usually we write something equals, but we can put equals something. You know, you can put it the other way. It's just as true, right? You can flip it around if you'd like. Okay, so numerator divided by denominator, 61456 divided by 2842 equals, okay, and it's going to be my answer, what, oh, green, 21.62. Now, what units does this thing have? Well, kilograms divided by kilograms. And then this is what's left. And that's exactly what we want, meters per second, because it's a velocity. So now that is my answer, or if you like, you could write it, oh, you know what, because we're going to write it in scientific notation. So that's my answer, but if you want to put it in scientific notation, we got to move that decimal over. So then I'll put it this way. This will be my final answer. My final answer for final velocity equals 2.16. And I could keep that to, I'll just put that 2 there so you see where it went. Okay, I could have just left it 2.16 times 10 to the first power. Okay, notice anything that's in the tens place is going to have the first power. Anything in the hundreds place is going to have the second power, right? And then don't forget the unit. If you write a number in scientific notation, don't forget the darn unit. Write your units, okay? And this would be my final answer. Okay, so remember that momentum, I forgot to mention at the beginning, has a positive or negative direction. So really what we should have done in all of these things is we should have been putting little plus signs because they were all going in the same direction. I wasn't concerned with that because they're all going the same way. When we have things going in opposite directions, it's a bigger concern. And obviously if you have positive velocities, if that's your positive direction, see right here, see how it says that direction is positive, okay? So if you have positive velocities, well, that will give you positive, okay, positive momentum, and then all these numbers will be positive all the way through, okay? So really, we could have put here the velocity is positive, but a lot of times when it's just positive, we leave it out. We leave out the plus sign. Okay, I can put a positive right there. It becomes more of a concern when we are dealing with objects going in opposite directions because this one's going positive. Let's say this one's going positive and this one's going negative. Okay, so they manage to stop each other. Okay, let's try it this way. Yeah. So positive direction, negative direction, and you can define that whichever way you want because it depends on the perspective you're taking. Okay, you can take the perspective if this is you, probably want to think that's positive. If this were you, that could be positive. So positive can be to the left, okay? And depending if you're dealing with more dimensions, it could be up or down, depending on how you happen to define it. Okay, so that's a good example of momentum. I'm going to do some more examples on a separate video, but this is the basics. If they're both going in the same direction, this is a pretty simple example. Conservation of momentum.
So what about recoil? Well, recoil has a lot to do with the conservation of momentum. It also has to do with Newton's third law, equal opposite reactions. Assume that a girl and a boy are skating on a smooth surface. Now these are really cool people with rollerblades on, and there are no external forces, at least no net forces. So they obviously have weight, but it's balanced by the normal force. So we can ignore that. They both start at rest, so what's the initial momentum? What's the total initial momentum? Think about it. One of them is behind the other. Skater C on the left, the boy, gives skater D, the girl, a push. So you might imagine if you push somebody that they're going to go moving away from you, and that is true. But remember about Newton's third law, equal opposite reactions? So if you push somebody, well, even if they don't try, they are automatically pushing back. Action, reaction. So you will wind up, the boy will wind up going the other direction. So how fast is he going to move? Well, you can calculate that using the recoil equation. You can find the final velocities of both of these rollerbladers. So after clashing with each other, both skaters are moving. They're no longer still. But then how is that a conservation of momentum? If the initial momentum was 0 and now they're moving, how does that make sense? Well, remember, one of them is moving positively, the other one is moving negatively. So we can define that any way we choose. And, just for fun, I'm just going to assign positive to the left. Why not? Just to make a change. So because the push was an internal force of the system, you can use the law of conservation of momentum, and you can find the skaters' relative velocities. You can find their velocities. So again, the total momentum of the system was 0 before the push. Therefore, it must be 0 after the push. We can choose a coordinate system so that positive is to the left. I just said that. And then the momenta, that's the plural of momentum. If you have one momentum, then you have two momenta of the skaters, are equal in magnitude but opposite in direction. Okay? So in other words, they're both going to have the same momentum, but I wonder what their velocities will be. Because it looked like he was a little more massive than she was. So just because you have equal momentum doesn't mean you're going at the same velocity in the opposite directions, remember. And that is an example of recoil. So how can we calculate the skater's velocities? Are the skater's velocities equal and opposite? Well, if you push somebody, then they push back, whether they like it or not. Action, reaction. So you'd imagine that it's equal force in both directions, so maybe you should have an equal velocity. But actually no, because it depends on the masses, the relative masses of the skaters. So here's a nifty little equation that shows you what the velocity of C will be if you know the velocity of D, the final velocity. It'll tell you the final velocity of C on the left if you know the final velocity of D on the right. If you know one, you can find the other as long as you know their masses. Now it's the ratio of their masses. It's negative because the velocity of one is in the opposite direction of the other. So it has to be put in negative. It's just the ratio of their velocities. Now in this case, remember C was the boy and D was the girl. So we'll solve for the velocity of C, which would be to the left, which is our positive direction. Using the velocity of D, which would be negative, it's to the right, okay, and when you multiply a negative times a negative, it'll give you a positive. And then the mass of the girl goes on the top, the mass of the boy goes on the bottom. And so even though the same force will be imparted on both of them, the less massive skater will have the greater velocity. Because think about it. If you want to have the same momentum, and if you have a lower mass, you have to make up for that by having a greater velocity, and vice versa. If you have a greater mass, you have to have a lower velocity to make them equal. I'm going to show you an example of this next time. So this is the equation for recoil. So you can think of recoil as being pushback, okay? If you push on something, it pushes back. And if there's not enough friction to stop you, you're going to wind up moving. Okay, so that's why we put them on skates to get a relatively frictionless or low friction situation. Okay, so this is the way to solve for one from the other. And remember, we could have just as easily used A and B, and we could have just as easily defined to the right as positive, and it would have been the same equation. It's just we would have been solving maybe for the other one. Okay, or whichever number you define as negative, well, when you plug that into this equation, the other one's going to come out as positive. So it works out. And it is okay to substitute the C's for A's and the D's for B's. That's fine. Now this is what our equation bank is looking like. It's getting kind of out of control. All of these equations we have used or are using right now, okay, in these notes. By the way, this even leaves out the universal gravitation, and it leaves out escape velocity. So this isn't even all the equations we've been using. So as you may have noticed, physics is a math-heavy subject. It's a way of understanding the world, and it turns out the language of our world is mathematics. Nobody ever says the full word. Try saying it, mathematics. People don't say it all the time. So those are the end of the notes on the conservation of momentum. I will later be doing examples of when the two objects are moving in different directions, one positive, one negative, and a recoil example. Bye. Ian!